All right, so thermochem, right? Finally, something new. That's a nice change. Next week is spring break, so you have 2 weeks to go over this, or a week and then a week of fun, whatever you choose to do. So this quiz for chapter 7, which is credit quiz 6, that won't be due until the Tuesday after spring break. Um, and I believe that's the 15th. Oh, the Ides of March. Okay. Anyway, so finally something new. What we're going to apply to our equation writing is heat. Heat is going to be like a new stoichiometric calculation we can do. We can look at the heat of a reaction and then quantify, okay, well, if I have this much octane, how much heat do I generate? How much energy? So the first part of the chapter is kind of going through the definitions of heat and work and all that good stuff. I got to tell you, to me, it was like, I don't know. I think I just really like calculations and math and not so much the definitions behind it, but it's good to understand what all that is. You definitely will see it again if you haven't seen it already in physics. But what I'm going to do is just sort of go through more of the chemistry and the calculations for this. So what I did go ahead and post the 3 videos for the chapter 7 notes. I did that on Sunday. I watched them again yesterday just to make sure that I thought they were pretty good. I felt like I kept making little mistakes, but when I watched the video, I was like, yeah, you did, but it's not like a glaring error. It was just tiny little, like writing a 2 instead of a 5 or something simple. So I think overall it came out pretty good. Today will help reinforce some things, but one thing in the 3 videos, the chapter doesn't really go through specifically what's called a thermochemical equation. And basically all it is it's a chemical equation like we would have written last semester in intro chem, but now attaching the thermo part, the heat, right, which is chapter 7. So the first couple, I'm looking at worksheet B. I'm going to try to go through as much of it as possible, only because I think it will be a good representation of a little bit of everything. Anyway, if we get to the end and I don't finish all of the heats of formation questions, just because they take a while to go get the table and all the values from the table, if that happens, not a big deal because there are other videos on that. But anyway, question number 1 for worksheet B, it says we've got aqueous sodium hydrogen carbonate, so NaHCO3, aqueous, reacts with hydrochloric acid, binary acid, right, HCl solution, and it produces aqueous sodium chloride, so NaCl aqueous, water, L, right, not aqueous because it doesn't dissolve in water, it is water, right, and then CO2, carbon dioxide gas. All right, and we saw in our equation writing chapter that carbonates, when they react with acid, they always release CO2. So the reaction absorbs, that'll be a key word that we have to start looking at here, 11.8 kilojoules of heat for each mole of sodium hydrogen carbonate. We want to write the thermochemical equation for the reaction. So basically, we just wrote the chemical equation. What makes it a thermochemical equation is when we attach the heat part of this. So first thing is, when heat is absorbed, it is an endothermic reaction, right? Heat has to go into the reaction. That's how I remembered it when I was, learning this for the first time. And I think I mentioned this in intro, which, if you remember, fantastic. But if you don't, that's okay, because it really wasn't a big part of intro. If it's an exothermic reaction, heat exits the reaction. If it's an endothermic reaction, heat goes in or is absorbed by the reaction. So when this process occurs, whatever it is that's occurring here, breaking bonds, forming new bonds, overall, this reaction is going to have to absorb, take in 11.8 kilojoules of heat. And so we write this delta H, enthalpy or heat of the reaction. And because heat is being absorbed, it's a positive sign. So 11.8 kilojoules. And again, I'll note here, it's endothermic. All right, so when your reaction is absorbing heat from the surroundings, then what happens is that delta H is going to be a positive value, and that's going to show you that it is an endothermic process. So when delta H is positive, it's endothermic, and then the opposite is true. If delta H is negative, that means the energy is being released, and that means it's an exothermic reaction. So if we look at another one, it says a propellant for rockets is obtained by mixing hydrazine, N2H4, and it tells us in the question that it's liquid, and N2O4, dinitrogen tetraoxide. And the reaction produces nitrogen gas, N2, because it's part of Hofbrinkel, and water vapor, so that means the water's coming out as steam. and it evolves, right, up 1049 kilojoules of heat when 1 mole of the N2O4 reacts. Okay, so back up in this first question here, I forgot to emphasize this, is that it was talking about each mole of sodium hydrogen carbonate reacting. And we only have 1 mole in this reaction equation. So we didn't really have to worry about that, but we are going to have to worry about that here because I know where this is going. And so I'll emphasize that here in just a second. First thing I got to do is balance the equation. I have the hydrazine, the dinitrogen tetraoxide. I produce the nitrogen gas and the H2O vapor, so steam, right? But it's not obviously balanced. When I look at this to just kind of start, I have 2 nitrogens, but they split and go to 2 places. So sometimes that's not the best place to start. We talked about that in intro. The hydrogen, I could start there. It's in multiples of 2, but I kind of know where this is going. I'm going to start with the oxygen. There's 4 oxygens here in the N2O4. All of that oxygen comes out as the water vapor. There's only 1 oxygen in the water, so I'm going to have to multiply that by 4. So I put a 4 in front of the H2O. And then when I look at this, I have 4 times 2, so 8 hydrogens. I'm going to check my hydrogens. On the reactant side, I only have 4, so I need to multiply the hydrazine by 2. So now I have 8 hydrogens matching my 8 hydrogens. My 4 oxygens matching my 4 oxygens. So the last thing, right, always save the one that splits for last, right? We got nitrogen showing up in 2 places on the reactant side, only 1 place on the product side. So now what we'll do is, yeah, okay, sorry, balance the nitrogen. I was doing something else in my head. All right, so for the nitrogen, I have 2 times 2, so 4, plus another 2 nitrogens here would be 6. So on the product side, to get 6, I'm going to multiply the N2 by 3. All right, and now I have a balanced chemical equation. Now, in this case, the delta H is evolving the heat, which means it's going to be a negative. Evolving means that it's released. So that energy is being released from this reaction, and it's releasing 1049 kilojoules when 1 mole of N2O4 reacts. All right, and that is what this does say, that there's only 1 mole of N2O4 in the reaction. And so that 1049 would be the energy released. Now, what I want to kind of, sort of suggest going forward is that this delta H value, like up above, all the molar coefficients were 1, so it was going to be a bad example. But moving forward, this delta H value is going to be a new stoichiometric conversion factor. And what I can do is take that delta H value and relate it to any substance, right? We kind of learned that back in intro. You can have any A and B, right? And now your heat can act as an A or a B. So we can ask questions like, okay, all right, we get 1,049 kilojoules of heat released when we produce 3 moles of nitrogen gas. What about if we release 6 moles of nitrogen gas? Okay. Or what if it's 1,000 grams of nitrogen gas, right? So that's where this is headed when we start doing some thermostoichiometry. But what's important to sort of recognize going into this is that your delta H value, I can compare it to any substance in the equation, but the 1049 kilojoules is released for every 2 moles of N2H4. So that 2 becomes part of the conversion factor. So I get that much energy when 2 moles of hydrazine react, or I get that much energy when 1 mole of the N2O4 reacts, or I get that much energy when 3 moles of N2 is produced. So when you're looking at kind of like a mole-to-mole ratio is sort of the way I think about it. You want to make sure when you're relating your enthalpy to either a reactant or a product that that coefficient is included. That's going to be really important. So the 1049 kilojoules of heat is released. It's negative when 3 moles of N2 is produced. It's also released, right, when 4 moles of water is turned into steam and released, right? So this is exothermic because it is a negative enthalpy, negative delta H. Unlike the first question, right? It was endothermic, heat was flowing into the reaction, it was absorbed. But in this one, the heat is evolving, meaning it's released, so that's exothermic. And so again, remembering exo means it's gonna have a negative sign. All right, for question number 3, and again, those are both thermochemical equations. We'll be looking at a lot of these in this chapter. And hey, right, finally something new. when number three says 1 mole of iron reacts with hydrochloric acid, 87.9 kilojoules of heat evolves. So again, that means it's released with the production of hydrogen gas and aqueous ferrous. I would put iron 2, right? Iron 2 chloride. Write a thermochemical equation for this reaction. So we're going to take solid iron, react it with hydrochloric acid solution. We are producing hydrogen gas, part of Hofbrinkel, another diatomic, and iron 2 chloride, which will be in the solution. And hopefully that looks familiar. That's a nice single displacement reaction. And just to balance here really quick, 2 chlorines, 2 hydrogens. So we need a 2 in front of the HCl. And it said that the heat released was 87.9 kilojoules for every 1 mole of iron that's reacted here. All right, so that again is our thermochemical equation. We've got our balance equation like we learned how to do in intro chem. And then our 87.9 kilojoules is going to be negative because again, the energy here is released or evolved. It comes out. And if the energy is exiting the reaction, right, it's coming out, that means that this is an exothermic reaction. So in the textbook, we talk a lot, or it talks a lot about sort of the system and the surroundings. And then what's unfortunate is that when you get into calorimetry, it talks about a substance versus a system. And that was the only thing when I was like rewatching my videos yesterday, I was like, oh, I should have been more clear about that because a system kind of has 2 different meanings. So, which is, it should just be one. But anyway, so imagine that we did this reaction in lab and we're in a test tube and we've got water present, right? Because these are aqueous, they're happening in water. What'll happen is that as the iron and the hydrogen transfer electrons and the hydrogen comes out as H2 and the iron goes in as an ion into the solution. As that process occurs, it's releasing energy, right? It's evolving energy. So energy is exiting the system. The surroundings, which is the water molecules for that aqueous solution, the surroundings are going to absorb that energy, right? Energy is never created or destroyed. So there's a transfer. So as this system, in other words, the reaction, is releasing this much energy, the surroundings, the water molecules are going to absorb that much energy. So the water molecules are going to heat up, right? And that's what we might remember from intro chem is that when we had an exothermic reaction, the test tube got hot. So the system is releasing energy, the surrounding water molecules are absorbing that energy. And as they take in that energy, they move faster, temperature reflects that, it goes up. All right, so there's a little bit of a distinction with calorimetry between a system and a substance, not to be confused with thermochem in general when it talks about a system and surroundings. The system is the reaction itself. The surroundings is whatever medium is taking place in. It could be an air where the air molecules, the surrounding air molecules are either heating up or cooling down, but a lot of times we're in aqueous solution, so it's going to be in water. All right, so those are thermochemical equations just to get us used to writing delta H values, the sign of delta H, and then relating that to whether it's endothermic or exothermic. Now let's take that and relate it to some stoichiometry. So ammonia, which is NH3, burns in the presence of copper, which is just a catalyst, which means it's not used in the reaction. It's just to help lower the activation energy, so it makes it go better. Anyway, ammonia burns and it forms nitrogen gas. So the burning, the combustion process, right? Oxygen is the fuel for fire. We've got the nitrogen gas and all the hydrogen comes out as H2O. And we've got a delta H value that's given. So without the delta H, it's just called a chemical equation. With the delta H, it's called a thermochemical equation. So thermo meaning the heat. Because it's negative, we know that this is an exothermic reaction, right? So heat is going to be released during that process. Now, the question says, what is the enthalpy or heat change when we burn 35.8 grams of ammonia? So what I want you to recognize is we used balance equations to do mole ratios, right? For every 2 moles of nitrogen, we react 3 moles of oxygen. But you also want to recognize that when you're asked for heat, this delta H value that's given is a conversion factor. It's a new constant that we have. It's information that we have. Every time I do one of these reactions as written, 4 moles of ammonia, 3 moles of oxygen, I release 1,267 kilojoules. Well, I don't have a mole of ammonia. I have 35.8 grams. All right, so what we're going to do is we're going to start with that mass. We have 35.8 grams of ammonia, NH3. And the first thing we always do, because I told you this will never steer you wrong, is to go to moles. So we're going to go from grams to moles to NH3. So I go to my periodic table, 14.01 for nitrogen, 1.01 for hydrogen 3 times. We get 17.04. So that's just the molar mass. We're familiar with that. And then what I'm going to look at here is kind of, the middle would always be the mole to mole ratio. What we're doing is we are going to get rid of our moles of ammonia on the bottom, right? So we want 4 moles of ammonia here. But instead of going to a B as a substance, our B is the enthalpy. So that means B is our H. So every time I react 4 moles of ammonia, I'm going to release 1,267 kilojoules. And that'll give us our enthalpy, right? That's our heat. Enthalpy, just another word for heat. So 35.8 divide by 17.04 times the 1267, and then divide by that molar coefficient of 4 for the NH3. And if I keep 3 significant figures, I get a negative 665 kilojoules. All right, and then the enthalpy change, right? We want to make sure and keep that negative in there because that's it. That is important. The negative is telling me that energy is released, not absorbed by the system or the reaction. All right, so the sign is important. So don't think, well, what do I need the negative for? You can have negative heat. Negative heat means it's being released. Positive heat would mean that it's being absorbed from the surroundings. But in this case, the reaction will be supplying heat to the surroundings. All right, so that's how we can use our delta H as, in stoichiometry. And so kind of, again, just kind of relating this to what's familiar. We had mass, that's familiar. We know how to go to moles, that's familiar. But what's new here is solving for heat. And the way that the delta H is reported to you is based on how the reaction is written. So I get 1267 kilojoules of heat released every time I react 4 moles of NH3. So it's really important to capture that coefficient of 4 for the NH3. If I had let that kept out that 4 and I just put a 1, that wouldn't be right. I don't get 1267 kilojoules for every 1 mole of ammonia. It's for every 4 moles of ammonia. All right, so it is kind of like we're doing a mole-to-mole ratio. It's just in this case, we're going to B, which is the delta H, but we still want to capture that 4, that coefficient of 4. All right, so that's doing some thermochem stoichiometry. Let's try another one. All right, so on the next page, it says we've got propane, which is the C3H8, is a common fuel, right? We use it in our gas grill. We want to, let me let somebody in here really quick. We want to calculate the grams of propane. All right, so grams that we would need to provide 369 kilojoules of heat. This is part A. All right, so this is the opposite of what we had for the last question that we looked at. In the last question, we had mass. We wanted to know how much heat. In this case, we have a target of heat. We want to know what mass. So we're going to basically start with our heat, use delta H to get to moles, and then go backwards to propane. So we're trying to provide, which means we're going to release the 369 kilojoules of heat in this reaction. What my equation tells me is that I'll release negative 2044 kilojoules, right? Kilojoules will go on the bottom for every 1 mole of propane, because it has that coefficient of 1 in front, right? Nothing in front means it's an implied 1. And then, like we know, if we're trying to get to grams, to get rid of moles and go to grams, we need the molar mass. So if I go to my periodic table and add 3 carbons and 8 hydrogens, I get 44.11. So if I take my 369 divided by the 2044 and then multiply by 44.11, I would need 7.96 grams of C3H8. Now, just as a note real quick, right, mass can't be negative. So if you had sort of lost that negative here with the 369, if you didn't put that in, When you divided by delta H, which was negative, you would have caught it, right? Because the sign of the enthalpy, that has to cancel out, obviously, because you can't have a negative mass. So 7.96 grams of propane, right? We know 1 mole of propane will give us 2044 kilojoules. We only needed 369 to be released. So we only need about 8 grams of propane to do that. So that was question A. Let's now look at question B. Question B says, how many liters of carbon dioxide gas? So this will be question B. We're at 27 degrees Celsius and 745 torr. Hopefully this is starting to sound like a gas loss question. And in this case, we want to release 25,500 kilojoules of heat. So again, we're going to start with our heat released. It's going to be negative because when it's released, it's a negative sign. 25,500 kilojoules of heat released. My thermochemical equation tells me I get 2044 kilojoules of heat released, but this time we're comparing it to CO2, right? Carbon dioxide is what we're looking for here. So I need to capture that coefficient. For every 3 moles of CO2, I get the 2044 kilojoules released. Now, what I'm going to do is I'm going to pause here for a second. So I'm going to take the 25,500 divided by the 2044 and then multiply that by 3. And I get 37.4 moles of CO2. And the reason why I stopped there was because I knew I was going to be going to gas laws, right? I knew that this was, we kind of talked about that. Whenever you see temperatures and pressures, you know it's a gas law problem. And what we're thinking about here is I've got one pressure, one temperature, the moles of CO2, right? So in my mind, I'm thinking I'm going to Pivnert. Pivnert's going to be my formula of choice. So I stopped here because moles, of course, that's my N. And so then if I want to continue, volume will be nRT over P. So my moles I just solved for, I should have 37.4 moles of my carbon dioxide, R 0.08206. Temperature I know has to be in Kelvin. So 27 degrees Celsius added to 273 would be 300 Kelvin. And then for my pressure on the bottom, just really quick, 745 divided by 760 to make sure it's an ATM. And what I get here to 3 sig figs is 0.980. All right, and so now there's my pressure in atmospheres. So I've got my moles of carbon dioxide at 37.4 based on the stoichiometry. I had a target of releasing 25,500 kilojoules. I'm going to release or produce 37.4 moles of CO2 when that happens. So there's my N times 0.08206, the ideal gas constant, times the temperature in Kelvin, which was 300, divide by the pressure in atmospheres, 0.980. And what I get here is 939.5. So I'm going to round that up to 940. But since I want 3 sig figs, I'll put the decimal on there to show that the 0 is a sig fig. So that would be my volume of carbon dioxide produced as I produce that 25,500 kilojoules of heat. All right. So in thermochem, right, we're taking chemical equations, we're doing stoichiometry just like we did, molar mass, gas laws, all that good stuff that we remember. Solutions will be in here too with molarity. But now we're adding this delta H as a new conversion step. And I guess, again, I just want to make sure and emphasize this. When you use your delta H as a conversion step, make sure you capture whatever that molar coefficient is in the balanced equation. So since we were looking at CO2, it was the negative 2044 for 3 moles of CO2. When we were looking at propane, it was the negative 2044 for only 1 mole of propane. All right, so just make sure you always capture that coefficient. All right, so one more here before we move on to something else. It says when aluminum metal is exposed to atmospheric oxygen, it oxidizes to form aluminum oxide. How much heat is released by the complete oxidation of 24.2 grams of aluminum? All right, that is an oxidation step, right? It's being oxidized by oxygen. So don't worry, don't get caught up in the terminology. It just means that this reaction goes 100%. So I've got 24.2 grams of aluminum, and I want to know how much heat is released. So again, aluminum is acting as the A, the heat is going to be acting as the B. So I have my 24.2 grams of aluminum. 26.98 is the molar mass from the periodic table. Then when I think about doing a mole ratio, it's 4 moles of aluminum. So I'm getting rid of my A on the bottom, and my B is the negative 3352 kilojoules, right? So again, that's my delta H as written. And I wanted to, again, make sure capture that molar coefficient of 4 for the aluminum. So 24.2 divided by 26.98 divided by 4, and then times 3352. And again, we don't want to miss that negative sign, keeping 3 sig figs, negative 752 kilojoules. And that is heat released. All right. Okay, so thermochem, we did a few examples there. Just be prepared. I think I remember one in the homework was a solution, so it had volume and molarity. Same idea, right? That's how we use molarity to get to moles. This one looked at gas laws. There's a couple in the homework that do gas laws. And then this one, I think a little bit easier because we're just looking at solids where we have a mass, molar mass to get to moles, but all of them are now incorporating that delta H as a as part of the stoichiometry. And I think that was probably good for some examples with thermochem. Now, the next big thing is Hess's law. And when I was going over this for video number 3 for the notes, I have to say, in my experience, and I don't know if I understand why, this one seems to trip up students, and I never understand why. I feel like these are so much fun. I feel like they're really straightforward. But the idea is, let me go back and kind of talk about this. The idea is that when we write a thermochemical equation, right? Like if I just use this one because it's here, 4 moles of aluminum reacting with 3 moles of oxygen make 2 moles of aluminum oxide. When that happens, I release 3352 kilojoules. If I only had half as much, like 2 moles of aluminum, 3/2 oxygen, and 1 mole of aluminum oxide, if I only do half as much, I'm only going to get half the energy. That always made sense to me. So when you look at Hess's law, the rules are that if you multiply a reaction by N, then you're going to take your delta H and multiply it by N. So if I multiply everything through here by a half and do half as much, I'm going to get half as much for the delta H. All right, so that's the first thing. Likewise, let's say I wanted to double this, 8 moles of aluminum, 6 moles of oxygen, 4 moles of aluminum oxide. So if I've doubled it, I'm going to double the delta H. So it'll be, not 60, but anyway, whatever 3352 times 2 is, right? So that would be doubled. Now, the other thing that you have to remember with Hess's law is what happens when you reverse the reaction. So I know that going this way, adding the aluminum to oxygen to make aluminum oxide, it's an exothermic process. It releases quite a bit of energy. If I think about reversing that and going in the opposite direction, taking aluminum oxide and decomposing it into aluminum and oxygen, if I reverse the reaction, it should be endothermic, right? If going one way is exothermic, then the other way would be endothermic. So this is the second rule, if you reverse an equation, then you're going to change the sign of your delta H. So those are really the only 2 rules that you have to remember with Hess's law. So here's the point, or here's what we're going to do with Hess's law. And again, I always thought these were kind of fun. They're like little analytical problems. We have an equation here, and I know that my camera's not great. It's 4 NH3 ammonia with 5 O2s to make 4 moles of just NO, nitrogen monoxide, and 6 moles of water. And we want to know what the delta H value would be for that. Then what we're given here is 3 thermochemical equations. And when I look at this, I've got N2 plus O2 makes NO. I get a certain amount of energy release, or no, that's absorbed. That's a positive sign. Again, not coming up too clear. Then the N2 plus H2 to make ammonia, releasing 91.8 kilojoules. Hydrogen plus oxygen to make water, releasing 483.7 kilojoules. So what you're tasked with doing here is using these 3 given thermochemical equations to figure out the thermochemistry of that target equation. all right, the NH3 plus oxygen to make nitrogen monoxide and water. So this is the target equation. This is the one we're trying to figure out. And what I'll do is I'll label this reaction 1, reaction 2, reaction 3. So here's what we're going to try to do. We're going to take these three equations and we're going to look for what's called what I call discrete substances. They're substances that only show up in one equation. So just as an example, the ammonia, when I look, it's not in equation 1. It is in equation 2, and it's not in equation 3. So if I'm trying to get my ammonia, I'm going to pull it from equation number 2. So I'm going to make myself a little note. This one comes from equation 2. When I look at the oxygen, oxygen's a little bit tougher because I see it in this first equation with the nitrogen, and I also see it in the second equation with the hydrogen. So that's going to be, I'm going to not worry about that one. It's kind of like when you do balancing equations. If there's something that comes from two different places, do that at the very end. Now let's look at the nitrogen monoxide. I see it here in the first equation, not in the second, not in the third. So the nitrogen monoxide is going to have to get pulled from equation 1. And then the water, not in the first equation, not in the second equation, but it is here in the third equation. This one's going to come from equation 3. So what I'm going to do is I'm going to manipulate equations 1, 2, and 3 so that my discrete substance is on the correct side of the reaction, reactant or product, right? It has to be on the correct side, and it has the correct coefficient in front. So first, let's look at the ammonia only because this is here. So let me look at the ammonia. All right, so I'm going to write all of my new equations down here. With the ammonia, I have 4 of them and they're on the reactant side. So I go to equation 2, right? Because that's where I'm going to be pulling this from. So the ammonia is going to come from equation 2. And when I look at that, number one, I've got 2 problems. You're going to first say, okay, I need 4 and I only have 2. Okay, so that means I'm going to have to multiply this reaction by 2, which means I'm going to have to multiply the delta H by 2. Right, that's what we were talking about. If you multiply through by some whole number n, that, or it could be a fraction like a half anyway, then also do the same thing with your delta H. So we multiply everything through by 2 because we want 4 ammonias. We only have 2 here. And we're going to have to multiply that delta H also by 2. So instead of -90, it'll be like -180, right? Then the next thing I look at is it on the correct side of the equation? And the answer is no. In my target equation, it's on the reactant side. In my given equation, it's on the product side. So I'm also going to have to reverse this equation. And that means I'm going to have to change the sign of the delta H from negative to positive. All right, so let me do that first. All right, so we decided for equation 2, we're going to reverse it and multiply by 2. So the 2 ammonias is now going to go to the reactant side. And the 2 is going to become 4. So we're going to have 4 NH3. I'm not going to worry about the states. Then my 2 reactants are now going to go to the product side. And I'm going to multiply by 2. So instead of 1 nitrogen, I have 2. And instead of 3 hydrogens, I'll have 6. So we flipped it, right? And if you want, I'll show that step. We flipped it. We had the 2 NH3s turning to N2 and 3H2. So I just reversing the equation here. So that means that delta H would be positive 91.8. All right, so when you reverse the equation, you change the sign. So again, going forward, making ammonia releases 91.8 kilojoules, reversing it and decomposing the ammonia absorbs 91.8 kilojoules. So the 2 ammonias became on the reactant side, the nitrogen and hydrogen go to the product side. Then what I did is I took that equation and multiplied it by 2. 2 ammonias became 4, 1 nitrogen became 2, 3 hydrogens became 6. So I'll take that 91.8 that I had and multiply it by 2. So I get a delta H here of 183.6 kilojoules. So that's how we can take a thermochemical equation, change the equation, and then figure out what the delta H will be. And why does that work, right? I remember like when I first started learning this, I was like, how is it that simple? And what we're going to see when we get to the heats of formation is that when we get these delta H values, it's because we're looking at, okay, nitrogen bonds being broken, hydrogen bonds being broken, and then forming nitrogen-hydrogen bonds. And overall, all of that together releases 91.8 kilojoules. So if you go in the opposite direction, where now you have to, instead of breaking nitrogen-hydrogen bonds and forming hydrogen and forming nitrogen bonds, like reversing it, then it makes sense that the energy is going to be reversed as well. So instead of releasing 91 kilojoules, it's going to absorb 91.8 kilojoules. Okay, but we'll look at that when we get to heats of formation. Okay, so the first thing I did was just deal with the ammonia. So now I've got my ammonia, it's on the reactant side, and I have 4 of them. All right, so my ammonia is all set with my target equation. It's right where it needs to be. Okay, so that first part done. Well, now let's look at the NO. All right, now I'm going to change pens. The NO, the 4NO, we made a note. It's going to come from reaction number 1. Okay, this first one here. So first, do I have the right coefficient in front? No, I only have 2 in my given equation and I want 4. So I'm going to have to multiply this by 2, which means I'm going to multiply the delta H by 2. Then I'm going to say, okay, is it on the correct side? And the answer is yes. It's on the product side. It's on the product side. So the only thing I'm going to have to do to equation number 1 is just multiply it by 2. So multiply by 2, I'm going to have, instead of 1 nitrogen, 2 nitrogens. 1 oxygen becomes 2 oxygens. And then on the product side, 2 nitrogen monoxides becomes 4. And my delta H is going to be twice what I had. And it wasn't that I changed the sign. It didn't show up clearly. It was a positive 180.6 times 2. So I get 361.2 kilojoules. All right. So I just multiplied that delta H by 2. Okay. Last substance is going to be the water. All right. So I'll change my pen. I've got 6 waters and it's coming from equation 3. So when I look at equation 3, the water doesn't have the correct coefficient in front. It only has 2. I need it to have 6. So I'm going to have to multiply this by 3, which means I'm going to have to multiply that delta H by 3. Second thing I always want to ask is the delta H on the right side? Yes, it's on the product side. So all I'm going to have to do to equation 3 is multiply it by 3. So 2 hydrogens will become 6 hydrogens. 1 oxygen becomes 3 oxygens. And then on the product side, the 2 waters will become 6 waters. And what I did here is I'm going to take that delta H, of the negative 483.7 and multiply that by 3 because I multiplied everything through by 3. So I get negative 1451.1 kilojoules. Sorry, it got skewed. There we go. Okay, now, whoops, sorry. So I've just looking at what I had, right? Oh, and it froze. I like to go back at this point, kind of double check everything here really quick. We decided that the 4 ammonias was going to come from equation 2, right? And so what we did with equation 2 is we flipped it, reversed it, and multiplied by 2. So 2 ammonias became 4, 1 oxygen became 2, 3 hydrogens became 6, and we took that negative, turned it into a positive, and then multiplied it by 2. So positive 91.8 times 2 was 183.6. The oxygen we said we'd worry about later. Then we looked at the nitrogen monoxide, which came from equation 1. It was on the correct side, but we had to multiply through by 2. 2 needed to become 4. So 2 nitrogens and 2 oxygens turns into 4 nitrogen monoxides. So I took that delta H of 180.6, multiplied it by 2, got 361.2. The water came from equation 3. It was on the correct side, but instead of 2, I needed 6. So I had to multiply this by 3. So 2 hydrogens became 6, 1 oxygen became 3, 2 waters became 6, and I took that delta H of negative 483.7 and multiplied it by 3. That got me the negative 1451.1 kilojoules. Now what I want to do is I want to add those 3 equations together and see what happens. So I'm just adding, let me see if I can put these into a box and make it a little bit clearer, right? So these are my 3 new adjusted equations. Now the ammonia should stay put because that's what I'm looking for in my target equation. And then the other thing I should have here is in my target equation, I should have 5 oxygens on the reactant side. So let's look. All right, in this equation on the reactant side, I just have the 4 ammonias. Now let's look at the next equation. I've got 2 nitrogens, but on the first equation, I have 2 nitrogens. So when I add these two together, all of my reactants, right, are equal to all of my products. So what I'm going to do is look for like terms that will cancel out. So what happens, the way you can think about it is this first reaction releases 2 moles of nitrogen, and then the second reaction consumes 2 moles of nitrogen. So that means I don't have any nitrogen when this is done. The first reaction releases 6 moles of hydrogen, and then this third reaction consumes 6 moles of hydrogen. So I don't have any hydrogen left when I'm done. The 4 moles of ammonia doesn't cancel out with anything here. Then I have 2 plus 3, so 5 oxygens not being canceled out with anything over on the product side. So those are going to stay put. There's my 5 oxygens. And then on the product side, what I have are the 4 NOs and the 6 H2O, again, not canceling out with anything. Now that should be my target equation. So if I scroll this down here really quick, hard to get it all in, but there's my 4 ammonias, there's the 5 oxygens, my 4 NOs, and my 6 H2Os. So since I added these equations together, I'm going to add those delta H values together. So I'm going to take the 183.6, I'm going to add it to the 361.2, and then I'm going to add it to a negative, remember, don't forget the negative, the 1451.1 kilojoules. So overall, my net delta H for this reaction is negative 906.3 kilojoules. And since we're adding, we want to keep the decimal place rule. So since everything was to the tens place, we're going to keep it to the tens place. So that's Hess's law. All right. And again, I always thought these were really fun, but I don't know. I think, I'm not sure, but some students have a harder time with this, maybe because there's just so much going on. But always make sure, look for the discrete substances. Like the ammonia only came from equation 2. Oxygen was going to be a bad choice to look at because it shows up in more than one equation. The NO, it came right from equation 1, and the water only came from equation 3. So learn, like figure out how to manipulate those 3 equations based on those 3 substances, and then add them together. Notice how the oxygen just fell right into place. As you reverse an equation, you change the sign. If you multiply through the equation by some number, do the same thing to your delta H value. And then at the end, when you add the equations together, like terms on both sides will cancel out, and just add up all your delta H's to get your net delta H for that target equation. So let's try another one on the next page. All right, so next page, we have a target equation of methane with ammonia to make HCN and 3 moles of H2. And we want to know the delta H. So again, that's my target. That's the one I'm looking for. I'm given 3 equations again, 3 thermochemical equations. All right, when I look first at the methane, not in the first reaction, it does show up in the second reaction and not at all in the third. So the methane is going to come from equation 2. All right, I'm just going to highlight that really quick. All right, so first thing I'm going to do here is I'm going to say, okay, with the methane, does it have the correct coefficient in front? Yes, right? It's 1 methane, 1 methane. So the coefficient is good. Second question is it on the correct side? Those are the 2 questions you always have to ask. The answer is no. I need it on the reactant side, but here it's on the product side. So I'm going to have to reverse this equation. So the methane is going to be the reactant. The carbon is going to be the product, and the 2 hydrogens as well. And so that delta H is now going to be a positive 74.9 kilojoules, right? So that's my first manipulation. Second thing I look at, I've got this ammonia, NH3, and the NH3, I see it in this first chemical equation, not in the second and not in the third. So this has to be coming from equation number 1. All right, there it is. And then I have to look at, sorry, my thing froze again. So let me stop and start again. So I have to say, okay, first is, does it have the correct coefficient in front? No. It's got a 2. I only want it to have a 1. So I'm going to have to multiply it by a half. All right. And then the second thing is it on the correct side? And again, no, it's on the product side. I need it to be on the reactant side. So we're going to multiply it by a half and reverse it. So when I do that, reverse, multiply by a half, the product becomes the reactant, but instead of 2, it'll turn into 1. So NH3. Oops, not plus. It goes to an arrow. That's the only reactant we have, right? So that product became the reactant. These two reactants become the products. Instead of 1 nitrogen, I froze again. Instead of 1 nitrogen, it's going to become a half, right? Because we're multiplying everything through by half. And instead of 3 hydrogens, it's going to become 3 halves hydrogen. So what happens to delta H? It's going to become a positive 91.8 because we flipped it. And we're going to divide that by 2 because we also cut it in half. So 91.8 divided by 2 is 45.9. All right, so there's my delta H for that new reaction that I wrote in red. All right, third equation. All right, if I look at the hydrogen, I'm going to save that one for the end because I see hydrogen in all of my reactions. So that one was like the oxygen in the last example. We're not going to worry about that until we get all the other ducks in a row, so to speak. The HCN, the hydrogen cyanide, that comes from this third equation. So that's going to be equation 3. All right, so again, same 2 questions. Does it have the correct coefficient in front? No, I want only 1. This one's got 2. So I'm going to have to multiply this one by a half. Is it on the correct side? That part's good. I want it on the product side. It's on the product side. So the only thing I'm going to have to do with this third equation is multiply it by a half. So 1/2 hydrogen. Instead of 2 carbons, I'm only going to have 1. Instead of 1 nitrogen, I'm going to have a half. And then on the product side, instead of 2, I'm going to only have 1 of the hydrogen cyanides. And that delta H is going to be cut in half. So it's a positive 270.3. I'll divide that by 2. And I get 135.2 kilojoules. I just cut it in 2. Okay, now this one's a little bit harder to see because they're not stacked like they were in the previous example. But what I'm doing is I'm going to add together this adjusted equation and this adjusted equation and this adjusted equation. So once I've made those adjustments, those are the 3 equations I want to add together. Now the ammonia, that shouldn't be canceling out with anything, but let's just check. There's no ammonia on the product side here or here or here. So the ammonia is going to stay put. So we're going to rewrite that. There's my ammonia. Then the next substance I had was the methane on the reactant side. Why is it so blurry? I think it froze in a blurry form. Oh, there we go. So the methane here, not on the product side, not on the product side, not on the product side. So methane's not going to cancel out with anything. It's going to stay put, the CH4. And that works because that's what we had up in our target equation. So that looks good. Now, the other thing I've got down here in this equation is I have a half of H2 and I have a carbon and a half of nitrogen. So I got to figure out where those things are going because they need to be canceled out because they're not on my reactant side. So let me look at the carbon first. I've got the carbon from graphite in this this adjusted equation 3 on the reactant side. And then I've got carbon on the product side in the second equation. So remember, if you have like terms on both sides, reactant and product, they're going to cancel out. So carbon's going to cancel out. Then when I look at the nitrogen, I have a half of nitrogen on the reactant side. In the first equation, I've got half of a nitrogen on the product side. So those two also can cancel out. Here it's in the product, here it's on the reactant side. So those are going to go away. So I release a half nitrogen, I consume half nitrogen. So my net use of nitrogen is 0. Now, when I go to look at the hydrogen, I've got a half here on the reactant side, and I have 1.5 plus 2. So I have 3.5 here on the product side. So when you look at that, you're like, well, that's not going to cancel out, but that's okay because I should end up overall with 3 hydrogens on the product side. So what I'm going to do is I'm going to simplify this. The half hydrogen, I'm going to take away half here, and I'm going to take away half up here. So instead of 3 halves, I'm going to take away a half and it's going to turn into 1. So 3/2 minus a half is 2/2, right? So it becomes 1 hydrogen. So instead of 1.5, I took away half and I only have 1 left. So now on the product side, what I have left that isn't canceling out because everything else on the reactant side is gone except for the ammonia and the methane is I have 1 plus 2. So I have the 3 hydrogens. And the other substance I have here is the hydrogen cyanide. All right, and so if I look, that is my target equation. I just flipped the orders of the hydrogen and the hydrogen cyanide, but that doesn't matter. It's the same 2 products. So I did do this right. I manipulated everything correctly. I've got everything canceled out the way it should for the target equation. So now what I'm going to do to get this delta H is I'm going to add the 45.9, the 74.9, and the 135.2. All right, so what I'm going to do here, just really quick on the calculator, again, I keep the 1 decimal place. So I'm going to have 45.9 added to 74.9 added to 135.2. And I get here, it's 256, but I'm going to go ahead and add the 0.0 to keep that tons place. So my thermochemical equation then is when methane reacts with ammonia, it produces 3 moles of hydrogen and hydrogen cyanide. And that delta H value endothermic is a positive 256.0 kilojoules. All right, so the next one, there's one more, and I know Hess's law, you might be like, okay, I got it. But Hess's law, I feel like doing one more is not a bad thing. Like I said, sometimes students have a harder time with Hess's law. So we're going to do one more here, and then we'll look at heats of formation. So again, I've got a target equation. I've got ethene, C2H4, reacting with hydrogen to make ethane, which is C2H6. All right, and this is, again, the target equation. And I'm given a bunch of equations here, 3. But you'll notice there's a lot of stuff in here that we're not going to need. I just need the ethene or ethylene, the hydrogen, and the ethane. And I got a lot of extra stuff here. So a lot of things are going to be canceling out. But again, it's the same logic. Don't be distracted by the carbon dioxide and the carbon monoxide and how all that's going to fit together. Just look for the discrete substances. So I'm going to start with my ethylene or ethene, C2H4. When I look, I see it in this first equation. I don't see it in the second equation or the third equation. So the ethene or ethylene is going to come from equation 1. Let me be consistent with my pens. So this is going to come from equation 1. So when I look at equation 1, ask yourself 2 questions. Does it have the correct coefficient in front? The answer is yes. Is it on the right side? Yes, it's a reactant. It's on the reactant side. So I don't need to reverse. Those are the only 2 things I can do. I can only reverse or multiply through. All right, and I don't have to do either here. So this one, I'm just going to actually keep it the same. I'm not going to do anything to it. Then when I look at the hydrogen next, it's deceiving. You might want to say, oh, that one I'll worry about later, but it's not in the first equation. It's not in the second equation. It's only showing up in the third equation. So that hydrogen is coming from equation 3. All right, so when I look at equation 3, what I can see here is the hydrogen is on the reactant side like I want, but in the given equation, I've got 2, and I only want to consume 1 hydrogen. So I am going to multiply this by a half. So instead of 2 hydrogens, I'm only going to have 1. Instead of 1 oxygen, I'm going to have a half. And on the product side, instead of 2 waters, I'm only going to have 1. And I'm going to also do that with my delta H. I'm going to take that 572 and cut it in half. Keeping the negative, it would be negative 286 kilojoules. All right. Then for the last piece, the ethane, the C2H6, this is coming from equation 2. It shows up right here. All right. And so when I look at this one, I say, okay, it has the correct coefficient, but it's on the wrong side. So I'm going to have to flip it. All right. So I'm going to write this up here. I'm going to reverse it. All right. So the 2 carbon dioxides will now be on the reactant side, along with the 3 waters. On the product side, I'll have that ethane, C2H6, and the 7/2 oxygen. And my delta H, I'm just changing the sign to positive 1550. All right, so now my 3 equations that I want to add together, I'm going to put them in boxes. The first equation we decided to keep the same. The second equation we decided to flip to get the ethane on the product side. And then that third equation, we just had to multiply everything through by a half. So there's my three equations I want to multiply together. Or not multiply, sorry, add. Okay. So methane stays put. Now let's look at this oxygen. Right, in the first equation, we've got 3 moles of oxygen on the reactant side. Where's that going to be canceling out with? Well, on the reactant side here, I've got 3 oxygens. On the product side, in the next one, I have 3.5 oxygens. And then on the reactant side, in the third equation, I have a half. So on the reactant side, I have a total of 3.5 oxygens. And on the product side, I have 3.5 oxygens. So my net use of oxygen again is 0. So oxygen's going to cancel out. Then on the reactant side, in my second equation, I've got 2 CO2s. And what I see is it's on the product side in my first equation. So first equation releases 2 carbon dioxides. The second equation consumes 2 carbon dioxides. So that's going to go away as well. Then the other thing I've got on the reactant side are 3 waters. And on the product side in the first equation, I've got 2 waters. And in the third equation, I have another water. So 2 plus 1, I have 3 waters on the product side, canceling out with 3 waters on the reactant side. So again, net use of water is 0. So all that water cancels out. So what do I have left? I've got my ethylene or ethene reacting with my hydrogen to make my ethane. That's the only thing that didn't cancel out at this point. So that is my target equation. So what I'm going to do is take my delta H for those 3 equations and add them together. So this one we kept the same. So I'm still going to keep that negative 1401. Then what I'm going to do is add that to a positive, because we had to reverse the equation, positive 1550 kilojoules. And then I'm going to add that to the equation down here that I cut in half, the negative 286. And what I get here is a delta H of negative 137 kilojoules. And on this one, I'm just going to go to the ones place because we didn't have anything past the decimal. And I'm going to assume that that 0 in the 1550 is a sig fig. So we'll keep it to the ones place there. All right, so that's Hess's law. I think they just take a little bit of practice. I don't know if sometimes students kind of get bogged down in the things that are going to cancel out and they try to figure out how those are going to balance, and maybe that's what gets them off track. So just always look for the discrete substances, right? All of the ethylene came from the first equation. Ask yourself the same 2 questions every time. Does it have the correct coefficient in front? Is it on the right side of the equation? Right? And then go to the next substance. Where did that come from? Well, that came from this equation. Wasn't anywhere else, right? The hydrogen only came from equation 3. It was on the right side, but instead of 2, I only want 1. So I need to multiply this equation given to me by a half. I need to cut it in half, right? So there's my 1 hydrogen that I want. And then the ethane only came from equation 2. It was on the correct side, correct coefficient, or no, sorry, it wasn't on the correct side. I had to reverse it. I made it go to the correct side. I made it become a product like I needed it to. So just make sure you end up with your substances where they need to be. Ethylene on the reactant side, 1 hydrogen on the reactant side, and then the ethane on the product side. Everything else, once that happens, should just all cancel out like you've seen in the last 3 examples. All right, and again, the rules are if you multiply your equation by some number, multiply delta H by that same number. If you reverse the chemical equation, you change the sign of the delta H. All right, now again, those delta H for the reactions, they're basically coming from bond energies. And so the other way that we can get delta H for the reaction is using what are called enthalpies of formation. Now for this one, on the quiz, there is a table that's posted. It's just actually copied out of a textbook. If you're doing your homework though, you may either want to print out that table to have it handy, or for me, I've got the entire big hard copy textbook. So, and I remember doing this a lot as a student, I have mine bookmarked. All right, so for me, it's the appendix, it's appendix 2. And what you have here, and you've got your enthalpies, your delta H, your delta Gs, and your S. Those are going to come later in Chem 2. So we don't need the second and the third columns, the Gibbs free energy and the entropy. We just need the delta H values. Delta H formation and kilojoule per mole. And the not symbol there is just to say we're at standard state, which is always the assumption. We don't have to worry about not being there until Chem 2. And they're organized by element. So like you've got magnesium, manganese, mercury, but you'll see how you may have to look in 2 different places to find what you're looking for. So let me show you how I use this. So for this question, number 10 on the worksheet, it says use the standard enthalpies of formation table to determine the enthalpy change for the following. We've got this reaction. We are going to consume 2 moles of H2S and 3 moles of O2, and we're going to produce 2 moles of water and 2 moles of SO2. Now, when I go to look for my H2S, you're going to say, okay, do I look for hydrogen or do I look for sulfur, right? Because both of those elements are in there. I always found that I looked for what I thought was the more unique or more rare. Like hydrogen's in everything, but sulfur's not really in everything. So I would go and look for the sulfur. That would be me. But you may have to check both. Like if you check hydrogen first and you don't find it, then go check the sulfur. So when I come over here to my sulfur, I have my H2S, but notice you've got H2S in the gas phase and you have H2S aqueous. So you have to make sure that you're pulling the right one. Am I doing this reaction in water or is this just in the gas phase? So if I go back to my equation, it's gas. I know it's hard to see with my webcam, but it's a gas. So I want to make sure and pull the delta H of formation or the enthalpy of formation for H2S in the gas phase. So I go back to my table. All right, my H2S in the gas phase is negative 20.6 for that heat of formation. So what I did just before I started is I went ahead and copied that over in my pen, of course, like, you know, negative 20.6, right? Next thing I do is I go to the oxygen, O2, gas phase. That one's easier. I know it's going to be listed under oxygen because there's no other element here. So I go and I look for my O2 again, want to be careful, right? Make sure O2, not O3, and in the gas phase, and what you'll notice is 0, right? So no enthalpy of formation, it's just a 0, that's standard. All right, now, next one is water, H2O, but again, make sure the phase, because we got liquid, we got gas, so make sure we grab the right one. So for this one, I also looked under oxygen, but when you look, sorry, I'm like doing 2 things at once. Yeah, okay. It actually didn't show up under the hydrogen. So it was good that I looked at oxygen. All right. So water, right? Not hydrogen peroxide. So I go to water, H2O, liquid, right? Not gas. We're in the liquid phase, negative 285.8. All right. So because that's a liquid, negative 285.8. And then I've got my sulfur dioxide gas, SO2 gas. So I go back to my sulfur column and I look for SO2 gas. So sulfur, SO2 gas. Over here, I got negative 296.8. So there's my SO2 in the gas phase, 296.8 negative. So what I did so far is I just wrote down my enthalpies of formation for each of my reactants and products. And remember, the units there are kilojoules per mole. So the problem here, though, is that well, it's not a problem, but I've got 2 moles of SO2. So I got to multiply the 296.8 negative times 2. I also have 2 waters, so that negative 285.8 needs to be multiplied by 2. The oxygen isn't going to matter because it's a 0, so multiplying 0 by 3 won't make a difference. And then I have 2 H2S, so that negative 20.6, I'm also going to multiply that by 2. So just make sure that you don't forget about the coefficients here. So remember, those heats of formation are given to you per mole. So if the equation says you got 2 moles, that's why you got to multiply it by 2. Now, the other thing that's important here is these are heats of formation. And that works with the water and the SO2 because those are being formed, right? They're being produced. But oxygen and H2S are being consumed, not formed, but taken away. So essentially what we're thinking is kind of like we talked about with Hess's law, is if forming H2S releases 20.6, then consuming H2S is going to absorb 20.6. So we're changing the sign. So what the formula is in the book is basically take your products and subtract out the reactants. You're basically changing the sign on the reactant side, right? Because instead of these being formed, they're being consumed. So instead of negative 20.6, it's a positive 20.6. So what you do is you look at your products first, do the sum. So I have the 285.8 per water released times 2 for 2 waters. So that's negative 708.6. And then I'm going to do the same thing for the SO2. It was 296.8 released times 2 SO2s. So that's a negative 593.6. So when I add that to the negative 708.6, I get a negative 1302.2 for the product side. All right, now kind of like breaking this down the middle. Now I'm going to look at my reactant side, right? The oxygen is a 0, so I don't even have to worry about it. And then for that hydrogen sulfide, H2S or dihydrogen sulfide, I've got the 20.6 negative times 2. So that's negative 41.2 kilojoules. All right, and that's for my reactant side. So what I'm going to do to figure out the delta H for the reaction is take products minus reactants. So I would have my negative 1302.2 and then minus that negative 41.2, right? Essentially, again, like we talked about, we're changing the sign. Instead of it being negative, it's going to turn into a positive, and we're showing that with the subtraction. All right, because instead of forming H2S, we're consuming it. So that's why the sign ends up changing. So I'm going to have a negative 1302.2 and negative minus a negative, that's going to become adding a positive, added to 41.2. So 41.2 minus 1302.2, since that one's negative, I get a heat of reaction of negative 1261 kilojoules. All right, and so that would be my delta H for that reaction. All right, so that's how we do heats of formation to get the delta H of this reaction. So we still would get a thermochemical equation here, right? We'd still get our delta H. So there's a couple of different ways of getting delta H. We can measure these with calorimeters. We can do this with Hess's law. We can do this with our standard heats of formation. Lots of different ways to figure out the enthalpy of a reaction. So I'm going to do one more of these on the next page, and then that'll probably take us to a nice place to stop. All right, so we got a couple more to do here. All right, so I've got the Fe2O3. So on my table, I'm going to be looking at the iron. And when I find the iron, I'm looking specifically at iron 3 oxide solid. All right, and in my table, I've got iron 3 oxide solid, which has an enthalpy of formation of 824.2 negative 824.2 kilojoules. All right, the carbon monoxide, I'm going to look under carbon for the carbon monoxide. Let's see, the state specifically is in gas. Carbon monoxide gas is a negative 110.5. All right, so I'm just writing the heats of formation. Then back to the iron, the Fe solid by itself has 0 for its enthalpy of formation. And then the carbon dioxide, going back to the carbon column, the CO2 is in the gas phase, and I've got negative 393.5. All right, so those are my heats of formation from the table, just grabbing them from the table. All right, then what I need to make sure and consider are the coefficients. So for the 393.5 released for carbon dioxide, that's per mole of carbon dioxide. Multiply that by 3 because, of course, we have 3 moles of CO2. The carbon monoxide, also coefficient of 3, so multiply by 3. And then 1 Fe2O3. All right, so first on the product side, I'm just taking that 393.5 times 3, and I get a negative 1180.5. Now for the reactants, I've got the 110.5 for the carbon monoxide times 3. So negative 331.5, and then added to a negative 824.2 for the iron 3 oxide. So when I add those two together, I get overall negative 1155.7 kilojoules. So when I go to find my delta H for the reaction, again, products minus reactants. So we're going to take that negative 1180.5 and minus a negative 1155.7. And that means it's going to become a positive. So minusing a negative, it's going to become a positive. So negative 1180.5 added to 1155.7, I get just slightly negative 24.8. So my delta H for this reaction, negative 24.8 kilojoules. All right. So always when you're doing enthalpies of formation, you want to get those enthalpies of formation from the table. And so, like I said, if you've got the textbook, it'll be in Appendix 2. If you don't have the complete textbook, there is a table posted. I think it's right above credit quiz 6 is where I put it. It'll have the table. It's basically a photocopy of another textbook I've used. And then just, again, making sure that when you go to use the table, you're grabbing the correct substances. This one may look a little strange here because it has ions in it, but it actually doesn't change anything. They have those tabulated as well. So just as an example, so I can show you the chlorine, heavy book. All right, I've got the chlorine ion that's dissolved in water. So if I go and look at my table, here's my chlorine. And when I scroll through here, there's my chlorine ion dissolved in water. Heat of formation, negative 167.1. All right, so that would be my heat of formation for the chloride. Then when I go to my hydrogen, I've got H plus also in solution, and that has an enthalpy of formation of 0. And then the hydrogen chloride, making sure is that a solution or a gas, and this one it's a gas, it's negative 92.3. All right, so negative 92.3, just making sure I grab the right number. Yep. So this one, a little bit easier because there's no coefficients to worry about. The delta H for the reaction, again, products minus reactants. And we're just going to take that negative, sorry, it froze again, the negative 167.1 and minus a negative 92.3. All right, and so the negative minusing the negative becomes a positive. So when I go ahead and subtract everything through, I get a delta H of reaction of negative 74.8 kilojoules. And that'll be my enthalpy for this reaction. All right, so sort of where it all began, everything in this chapter is sort of new. Remember that if your delta H is negative, it's an exothermic process. And it means energy of the system, which is the reaction, is released to the surroundings. So if we did this, dissolved the HCl in water, right, and those ions dissociated, we would feel the test tube get hotter because it's releasing energy as that occurs. Enthalpy, delta H, right, we can get those using those enthalpies of formation. We can get those through Hess's law like we practiced earlier. And we also can get them from doing calorimetry experiments, which we will look at in the lab. Those are also kind of fun. And once we have the thermochemical equation, we can do some stoichiometry. That's also where we started, where we saw that delta H can be used as a conversion factor. All right, so make sure when you're using your delta H in your stoichiometry, when you relate it to whatever substance it is that you're looking at in the question, in this case, it was the aluminum, you capture that coefficient, right? You get that much energy released for every 4 moles of aluminum. So when you do that conversion, make sure you capture the coefficient. And then the last thing in the chapter, it really goes into specific heat calculations. And there weren't any on this particular worksheet, but there are on the other worksheet, as well as in the part 1 video for the notes. So there's definitely a lot there to keep you busy with heat capacity, specific heat capacity, endothermic, exothermic, thermochemical stoichiometry, Hess's law, heats of formation. And it's all new, but I hope you all have a very wonderful break next week. I'll see you back in 2 weeks. Anybody have any questions for me?